Good evening, everyone. Today, I'm very happy to have Dr. Yinxiang Zhang, who is an assistant professor in the Department of Computer Science at Ohio State University. His research topics range over various fields in security, including cloud and mobile security, hardware-assisted security, user authentication, and anonymous communication. He's known for his work in side channel attacks and defenses in multi-tenant cloud computing as well. I'm looking forward to your talk, Dr. Zhang.
Thank you very much for the introduction, and thank you everyone for coming. I'm Yinxiang Zhang from Ohio State CIC department. Today I'm going to talk about cache memory attacks in clouds and mobile devices. Maybe some of you or all of you have never heard of the term cache memory attacks. That's okay, because I coined the term myself. Well, but probably you have heard of the term side channel attacks or row hammer attacks. Here I'm using the term cache memory attacks to refer to a set of attacks that involves the hardware CPU cache or the hardware memory. Okay, so before we go on to talk about the attack itself, let's just try to bring everybody on the same page. So here I'm showing a diagram of the computer, a processor of a computer, and also the DRAM memory. I hope you can see the DRAM memory here. Well, it's not showing here, but anyway. Okay, so here I'm showing two processor packages, and within each processor package, there are at least two CPU cores. And on each CPU core, there are two logical cores. And this logical core is enabled by the technology called simultaneous multithreading or hyperthreading. Okay, and attached to each core is a set of caches, and particularly there are L1 instruction cache, L1 data cache, L2 cache, and those cores are connected to a single last level cache or LLC. Okay, this is within one CPU package, and there might be multiple CPU packages on the computer system, and those packages are interconnected with the QPI technology, and with the integrated memory controller, they are connecting with the DRAM module, which the DRAM should be showing here, but for some reason it does not show here. Okay, so this is the hardware cache and memory system that I'm going to talk about today. Here I want to emphasize that the multiple processes supported by the same operating system will share the entire cache and memory hierarchy, and this could be a security problem. Okay, so what kind of scenario am I talking about here? Well, one scenario that comes to mind is cloud computing, right? In the cloud computing scenario, multiple tenants, they can run virtual machines on a shared computer hardware, and therefore they can share the same CPU cache and hardware memory. And another scenario is the mobile devices. On the mobile devices, it is possible to have multiple applications that do not trust each other, and then they run on the same device, but also share the memory and the cache system. Another scenario here is the browsers. So the JavaScript applications can run on the browsers and share the same CPU and memory hierarchy with the other component of the computer system. Okay, so in this talk, I'm going to highlight three different types of cache memory attacks. And we all know that there are three aspects of security. They are confidentiality, there are integrity and availability. There are different types of attacks, of cache memory attacks that illustrate the idea of confidentiality attacks, integrity attacks, and availability attacks. And particularly, I'm going to focus on the cache-based side channel attacks, which is one example of the confidentiality attacks. And also, I will talk about the row hammer attacks, which is one example of the integrity attacks. Actually, we also have a work focusing on the availability attacks, in which we show that one virtual machine can conduct this memory denial of service attack against other virtual machines in the public cloud. And for time's sake, I cannot cover this type of attack in this talk. So the first attack I'm going to talk about is the confidentiality attack, which is, in other words, cache-based side channel attacks. Before I can explain to you how this type of attack can work, let me try to go through this example and show you how memory access pattern can leak information. And you can see here, this is a very simple C program. I believe everybody here can only need three seconds to understand what this program is doing. Okay, it's very simple. Basically, this main program will take an integer as an input, as an argument. And depending on whether this integer is an odd number or even number, a function called inc will be called. Okay, this is the function body of inc. And then a variable b will be assigned the value of a and then return 0. Assuming that here, the input a here, the variable a here is the sensitive information that the attacker wants to learn. Okay, and here we want to show that the attacker can learn one bit of information of this variable, which is whether this variable is an odd number or even number. So how could the attacker do that? Well, if we decompose this program using and represent it as control flow graphs, and here we can see that this program can be decomposed into 3 basic blocks. And the basic blocks on the right may be called or not, depending on the value of a. Therefore, if the attacker has some way to tell whether the execution path on the right, well, that's on the right, on your right, on the right has been taken or not, he can learn the 1-bit information of the sensitive variable a. Okay, but how could the attacker do that without, well, dynamically tracing the program execution? So the answer is that the attacker can do that by cache-based side channel attacks. So let's further, compile this code into assembly language here. Here in this, there are still the same 3 basic blocks. And before each line here, this is the relative virtual address of each instruction. And we can see in this example, it so happens that these 3 basic blocks are stored in 3 cache line aligned and cache line sized memory blocks. So what is a cache line sized and cache line aligned memory block? Well, a cache line sized and cache line aligned memory block is usually of 64 byte, and one of the byte is being read by the CPU. One of the byte in this block is being read by the CPU. The entire block will be fetched into the CPU cache. Okay, this is what I mean by one memory block. And you can see in this example, it so happened that these 3 basic blocks are stored in 3 different memory blocks. Okay, and then if the attacker can learn using cache-based side channels whether the basic block here on the right has been fetched into the cache or not, and in this way the attacker can learn the execution path of this program and then learn the 1-bit information about the sensitive input A here. Okay, this is the key idea of cache-based side channel attack. There are multiple ways to conduct the so-called cache-based side channel attack, and the 2 most prominent attacks are, prime probe attacks and the flush reload attacks. The prime probe attacks assumes that the attacker and the victim share certain cache sets. Okay, this is a typical scenario. But in order to conduct this attack, the attacker needs to know the virtual to physical mapping of the victim. He needs to know which cache set is being shared with the victim, which cache set is not. Okay, and the other type of attack is called flush reload attack. And the assumption of this attack is a little bit different. It assumes that the victim and the attacker share some cache line, and this is possible if the attacker and the victim share some physical memory. And if they share same physical memory, and the memory blocks on those memory pages will be shared by both parties. And it's just very typical for 2 processes running in the same operating system. They share the same library code. Okay, so in this talk we are going to focus on the flush reload attack, but I have also been working on the prime probe attack before, but just to illustrate the idea of cache side channel attacks, let's just focus on the flush reload attack. Okay, the idea of flush reload attack is like this. There are 3 steps: flush, reload interval, and the reload. So in the flush phase, the attacker will try to use the CL flush, which is the instruction, unprivileged instruction on x86 platforms. The attacker will use self-flush instruction to flush out a certain memory block outside the cache. So basically, the effect of this instruction is to make sure certain memory blocks in the shared memory page does not exist in the shared cache. Okay, so this is the effect of self-flush. And then the next phase is called flush reload interval. And during this period, the attacker does not do anything, just wait for the victim to make use of the shared CPU cache. Okay, and if the victim somehow access the shared memory page, then the memory block, here I mean the cache line size and aligned memory block, will be loaded into the cache after the victim has accessed this memory block. Okay, and then in the next phase, which we call the reload phase, Okay, in reload phase, the attacker will try to read from the same memory block, and also time the duration of this memory read. And this duration is very long. That means the memory read is actually from the memory, and that also means the victim did not touch this memory block during the flush reload interval. But on the contrary, if the reload is very fast, then that means the reload is from the cache directly, and that also means the victim during the flush reload interval has somehow touched this shared memory page. And this is how the attacker can learn certain cache line has been used by the victim or not during a certain period of time. So this is called a flush reload attack. We have done several works along this line, and one of the paper we published using flush reload attack was back in 2014, which was a CSS paper describing three different flush reload attacks in the public cloud. Okay, we demonstrated the attack in the public clouds, and we particularly showed three different attacks. The first attack is called password reset attack. And in this attack, we particularly try to demonstrate using the flush reload technique, the attacker can learn when exactly an execution path is taken by the victim. And the second example of the attack we show is that the attacker can infer the sensitive user data. And in this example, we show that using the flush reload attack, the attacker can learn how many times an execution path is taken. And in the third attack, we show that we can use this technique to break the SAML-based single sign-on service in the public cloud. And particularly, we want to use this example to show the attacker can use flush reload technique to learn whether an execution path is taken or not. So I'm not going to go through all these examples, but I will show you how the first attack, the password reset attack, works, just to give you some idea about the attack. Okay, so you know that when you forget your password, what you do is to go to the website of this website and try to click on the forget password button. And what happens here is that a pseudo random number generator will be used to generate a random token, and that will be sent to you via email. And once you get the email, you can click on the token or use this token to authenticate to the web server again. Okay, so this is what happened. And some application implementation, like the PHP pseudo random number generation, they only use entropy source from system calls like get time of day. Okay, this is bad design choice, but this is the fact back in 2014. So the PHP application usually only use get time of day or time function to get this as a source of entropy to generate the pseudo random numbers. And so let me show you how to use the flush reload side channel to learn to predict the random number that is generated by the pseudo random number generator here. So here we consider a scenario where the attacker and the victim share the same operating system, and this is true in the public platform and the service cloud. And here, the attacker will act on behalf of the user and try to reset the password of an arbitrary account. And what will happen is that this pseudo random number generator will be used to generate a random token. And then during this random number generation, get time of day function will be called several times. And the attacker can use the flash reload technique to learn when the get time of day function is being called, and then call this function immediately after this incident. So the attacker can get the same result as the victim. And using the same value, the attacker can use the open source pseudo-random number generator implemented in PHP to predict the token with high accuracy, and then use this token to reset the password. So this is just one example of how this type of attack can be used in practice. Well, so this work in the public cloud was done 2 years ago, and more recently, I have been working with my students to conduct a flash reload attack on ARM and Android devices. So you might be wondering, well, what is different on ARM? Well, there are several technical challenges on ARM that makes flash reload a lot hard. Flash reload attack very difficult. And in fact, the first paper describing flash reload attacks, which was published in 2013, the author claimed that it is impossible to do flash reload attack on ARM because of, well, the following reasons. The first reason here is that there is no unprivileged CL flash instruction. This instruction is essential to the flash operation. Without this instruction, there is no way to flush out certain memory region or memory blocks out of the cache. And the way we deal with this problem is by using a system call called clear cache. So why there a system called clear cache help you flush the cache region? The reason is that on ARM devices, the ARM processor does not support coherency between the instruction cache and data cache. That is the design of the ARM processors. And because of that, in order to support self-modifying code, the operating system must provide a way to allow the application to call a system call and then flush certain region of the cache, or certain region of the memory out of the cache, in order to support the self-modifying code. And we just exploit this system call in place of CL flash instructions. Okay. And the second difficulty is that, well, unlike on Intel or AMD processors, the cache coherency and inclusiveness of ARM processors are not very well reported or documented. So we do not know exactly how the cache coherency protocol and the inclusiveness of the last level cache to the L1 caches are implemented on the ARM devices. Well, so in order to effectively conduct side channel attacks on ARM devices, we use the timing channel to learn what is the effect of the cache flushes. So in other words, we want to learn whether the clear cache system call will flush the local L1 cache and also the shared L2 cache, which is also the last level cache on ARM. Okay, which cache will be flushed by this instruction? By this system call. And also, we also use the timing channel to learn whether the L2 cache is inclusive to L1 cache or not. So this information are not reported by the document, and we have to use the timing channel to learn such information. And the third difficulty here is that, well, because the clear cache system call is to support self-modifying code, and essentially it only flushes the instruction caches. So that, remember, the flash reload attack requires to flush certain memory region out of the cache first and then reload it back. And because it can only work on the instruction cache, so we in other words, we have to use the, during the reload phase, we have to execute some function to load the data, to load the memory block into the instruction cache. Well, that's a problem. That's a problem because in order to conduct this attack, that means we need to understand the semantic of this program. Otherwise, we need to understand what arguments will be used by this function and what are the global variables that will be used inside this function in order to call this function outside the victim program. And also, because the reload phase will be used for timing purposes. So in other words, the attacker needs to time how long it takes to do the reload. And if the reload is executing the entire function, it may take a lot of time. You know what? I'll stand here. Okay. Okay, it will take a lot of time, and actually the execution time of a function may vary from time to time. So it is not ideal situation for the flash reload attack. So what we do in this paper is that I just want to focus on this part in this talk to show you how we can do the reload with only the instruction cache. So here, what we do here is we learn from the idea of return-oriented programming. So basically, we want to find several gadgets in the shared library. The gadgets basically is just one instruction that will change the control flow back to the original program. And we find several such gadgets in the shared library. And those gadgets are located in the memory blocks that we want to monitor, the detector wants to monitor. And in the attack program, which is the Android application, we construct this reload phase in the following ways. We construct a chain of entry point of these gadgets, and then we jump to each of these gadgets in turns. And once we jump to one gadget, and we will execute one instruction and then return immediately from that gadget. And in this way, we can try to load some of the memory blocks into the shared cache without executing the entire function. So this is the basic idea of the return-oriented reloads. And then we just time how long it takes to jump to the three gadgets, and then the overall time of the reload will be used to determine whether the memory blocks associated with the three gadgets have been used by the victim during the flash reload interval or not. Okay, so we can use all the indirect control flow transfer instructions on ARM. This table shows that on ARM v7 there are so many indirect control flow transfer instructions, and on ARM v8 there are so many of them. So for instance, we find two gadgets in the clock get time function in the standard libc library, and then we can construct the Android app as shown in this figure to make use of these two gadgets to learn whether the victim has called this function clock get time of day during the flash reload interval. Okay, so any questions so far?
I have questions about the shared memory pages.
Okay.
So in the case of the libc.so, so maybe different application may see the different memory pages for the same shared library because of
we need to use the mic so that we get a question, please.
So I have a questions of the libc.so, those shared memory pages. So maybe the different application may see the different the memory footprint for the libc.so. For example, if there is ASLR, then the code pages are always different. So
So in the attacker program, you can arbitrarily load any library that you can access, right? You can load this library explicitly and access the library pages, and as long as those libraries in the same operating system, it is shared with the victim.
Oh yeah, but the memory footprint when it is actually loading, the dynamic loader is actually gonna change the both code pages and data pages. For example, if there is pointers, then the pointer values are always different. And I don't know whether
we only focus on the static pages, code pages. We cannot. As long as the one process changes the content of the shared page, they're no longer shared. So we cannot use flash reload attack on those pages anymore. But we can. But for the static pages, like the static library pages, we can use this technique to do the attack. Does that make sense?
Yeah, but even for the static pages, in the loading time, it's gonna be patched. It's gonna be changing.
It's going to be changing, but we can reach a certain stable point because the attacker can control when to start this attack. The attacker can after fully loading this library and then can start this attack, right? So because the attacker has full control of this shared library on his side, so this type of noise does not matter. We did not observe
Yes.
difficulty in practice.
Yes, I see.
Okay, so I hope that answers your question partially.
Yeah, so I haven't really have a very the extensive experiences in the what are the memory footprints for the shared library, but the I see. Yeah. So
Okay.
it may change it depending on the use cases, I guess.
Well, I guess my answer is that in practice we do not find it's a very serious problem because the attacker can determine when it starts to load the library and when it starts to do the attack.
I see.
So the attacker has full control of this memory footprint. Okay, so so the next thing I want to talk about is that given the flash reload attack, what can we do on the ARM devices? Well, actually, we try to show two types of attacks. Well, it's not really attacks. Two types of capabilities that are enabled by this flash reload side channel on ARM devices. And the first one is to detect the hardware events. And here I'm showing that this is how the touch screen event is dispatched to the rest of the operating system, and we can directly use the flash reload attack to monitor a function called input sync. And then using this method, we can learn when the touch screen event happens. So we can generate a sequence of interrupts that are generated by the touch screen events. So what is the purpose of doing that? Well, remember there was a Auckland 16 paper, and in this paper they show that by reading the proc file system, they can learn the sequence of interrupts, and using this sequence of interrupts, they can infer the log pattern. Infer the user's log pattern. So here, we know that the proc file is very easy to be blocked from the applications, and without the proc file interrupts files, we show that it is still possible to regenerate this time series, the interrupt time series, and finish this log pattern attack. Okay, so. And also, we try to show another type of category of attacks, which is tracing the software execution. And here we showed in this example, we show how the display when the display is updated, what function is being called in the Android devices. And particularly, we try to flash reload one function called post frame buffer. That is used in the Surface Flanger series, and by doing so, we can learn when the display is updated. So we particularly show that using this technique, we can learn when a push notification arrives to the device, okay, and then when it disappears. And we can also show, and using this information, we can try to infer users' private action. And another example here is that this is a Discover app, and there is a blinking cursor here, and we show that because blinking cursor will blink twice every second, and here we show that using the flash reload channel, we can see when the cursor blinks. And further, if whenever a user try to input the password here, every time the user touch one of the keys in the software keyboard, the display will be updated, and we can see from this can be observed from the flash reload side channel as well. And this information can help us can help the attacker learn the inter-keystroke information. Okay, so to summarize the side channel attacks here, is that we know that there are some known targets we can use the cache-based side channel to learn the software and hardware-based events, and also use this side channel to learn the cryptographic keys in the RSA encryption, algorithmic encryption, ECDSA, AES, and DES. And the similar attacks has been demonstrated in the cloud systems, and there has been cross-process attacks, cross-container attacks, cross-VM attacks. And it has also been shown using JavaScript, the attacker can conduct a similar cache-based side channel attack, but not flash reload. Okay, and in our work, we show that a zero permission application can conduct a flash reload attack on mobile devices. Well, this is about the cache session attack, a very high-level overview of it. The next topic I'm going to talk about is the integrity attack, and particularly, I mean the row hammer attacks. So this is the architecture of DRAM. You can see that the processor will interact with the DRAM using memory channels, and within each memory channel there are multiple DIMM, and for each DIMM there might be two sides, and one side is one rank. And on each rank there are multiple chips, and on each chip there are multiple banks, sometimes 8 banks, sometimes 16 banks, and within each bank there are multiple rows and multiple columns. Okay, this is the basic DRAM architecture, and it has been shown by previous work that by repeatedly opening and closing a row enough times within a refresh interval will induce some disturbance error in adjacent rows. So what that means is that if you have a program access one row and then access another row and do that in turns, and if you do that frequently enough, it is possible to induce some errors in the neighboring rows. This is the DRAM the disturbance error. So a row hammer attack is basically hammering DRAM rows to induce the memory errors on purpose. Okay, and the row hammer attacks can be conducted very easily by using only five instructions. Only five instructions here. Like the first instruction is to move to read some data from one row, and then the second instruction is to read data from another row, and then use CL-flush instructions to flush the memory from the cache, so that next time if you read the same data, it will reach the DRAM. Okay, and in this way, the attacker can effectively induce memory errors. And there's another type of attack called double-sided row hammer attacks. This is more effective. So basically, if you frequently access two neighboring rows of one victim row, it will greatly increase the effectiveness of this attack. And in this example, as long as the attacker can access the two rows that are close to the victim row, it has a great chance to cause bit flips in the victim rows. Well, so we had a paper published at Unix Security 2016. This is with my grad students. And in this work, we have two major contributions. And the first contribution is to reverse engineer the DRAM addresses. Because the DRAM, the physical address will be mapped to a certain area in the DRAM, but this information is not disclosed by the DRAM vendor. Therefore, we try to use the timing channel to learn such information. So that is, we can use timing channel to learn which physical address will map to which row in which bank of the DRAM. And with that information, we can conduct effective double-sided row hammer attacks. Okay, and the second contribution is that once we have this effective double-sided row hammer attacks, how to exploit such row hammer vulnerability in the cross-VM setting is the question that we want to explore. Okay, so today I'm only going to focus on the second part, how to exploit a row hammer vulnerability in Xen cross-VM settings. So we particularly show that we can do the cross-VM row hammer attacks on Xen Para-Virtualized virtual machines. And this diagram shows the Xen Para-Virtualized Memory Management. Here, given a virtual address within the guest VM, okay, the address can be translated by walking through the full level of page tables. And what is in the page table entry is the physical address. Is real machine address. And this page table is stored within the guest kernel space. So it can be read by the guest kernel. But the Xen hypervisor will set those page tables as read-only, so that the guest kernel even though it is malicious, it cannot directly modify the content of these page tables. Okay, this is basic of the security. This is the basis of the security of the Xen Para-Virtualization. So, well, you know that the guest kernels will have to frequently update the page tables. But how to do that? Because the page table is read-only. The way to do so is by issuing hypercalls. And the hypervisor, upon receiving the hypercall, will check whether this request is legitimate. And if so, the request can be granted. Otherwise, the request will be rejected. Sorry, it doesn't work well. Okay, otherwise the request will be rejected. So, how do we exploit the Rollhammer attacks to break the isolation enforced by the Xen memory management? Well, we showed that we can conduct a page table replacement attack. Here, I'm showing a page table that is within the guest kernel address space. And here, a virtual address will be translated into a physical page that is mapped to is controlled by the attacker, is within the attacker's kernel address space. Okay, so everything inside this dashed lines, dashed boundary, is within the attacker's memory space. So here, what we want to do next is to create a forged page table. Okay, create a forged page table, and the entries within the forged page table can be an arbitrary value. So the forged page table can point to an arbitrary memory page on this computer. It can be a page that is controlled by the hypervisor, or a page controlled by another virtual machine. Okay, so there is a special requirement of this forged page table. Okay, the machine address of the forged page table will be different from the original page table only by 1 bit. Okay, and then we find another vulnerable page. So what is a vulnerable page? Rollhammer attacks are more or less predictable and repeatable. So if we find 1 bit that can be flipped by the Rollhammer attacks, it is very possible that it can be flipped again in the future. So we can we can conduct the Rollhammer attacks within the attacker's address space and try to identify one of the vulnerable pages. Okay, and then the vulnerable bit here. Okay, the vulnerable bit here has some special requirement. The vulnerable bit will fall into the region of one of the entries in this page, and this vulnerable bit will be the same as the bit that the forged page table is different from the original page table. This is the bit that is vulnerable to Rollhammer attacks. And the next step to do is to copy the content of the original PMD. Okay, to copy the original content of PMD to the vulnerable page, vulnerable page, and we call this vulnerable page as shadow PMD. Well, then because these two pages are identical, we can use a hypercall. We can use a hypercall here to replace the shadow PMD. To replace the original PMD with the shadow PMD. So now the shadow PMD will become part of the page tables used by the kernel because they are basically identical. This type of request can be granted by the hypervisor. And the next step is to conduct the actual Rollhammer attacks here. So after Rollhammer attacks, the bit can be flipped. The vulnerable bit will be flipped. And then originally, the entry in the shadow PMD was pointing to the original page table, but because of the bit flip here, it will be pointing to the forged page table. And this process will not involve the hypervisor, so the hypervisor does not know the page table has been changed. So from now on, the attacker can access this arbitrary memory page using this virtual address. And what's more here is that this forged page table can be written by the attacker. So the attacker can repeatedly write different values here in the forged page table and try to access different pages in the shared system. Well, this is the basic idea of the cross VM rowhammer attacks, and I just want to briefly mention one example here. So in this example, we show that the attacker can use the rowhammer attacks to compromise the OpenSSH server. So in this example, the OpenSSH server will use the PAM-based authentication method. So it's basically password authentication. Here we can see the figure on the left shows that shows the code, the original assembly code. So basically, when the user tries to authenticate himself, PAM authenticate, this function will be called, and the return value will be stored in the EAX. And depending on the value of EAX, if the value is 0, that means the authentication was successful, and otherwise it will jump to the error handling process. And the machine code of call PAM authenticate is E8-1B74FD and FF. Okay, and we can simply change the value of this machine, the 5 bytes machine code, into B8 followed by zeros. And this is the machine code of move 0 to EAX. So basically, we are moving a value 0 to EAX. And once we test the EAX with EAX, we'll get the 0 for sure. So we will bypass the authentication. This is a very simple idea. Actually, once you can change the content of the memory, there's a lot of things you can do. So just to briefly recap the attack steps. First of all, we'll do the page table replacement attack, and then once we can gain arbitrary memory access, we will enumerate all the memory pages on this shared system, and until we find the pattern, until we find an instruction with the same pattern. This is called PAM authentication. And once we have found it, we'll just replace this 5 bytes with a different 5 bytes. Okay, this is the basic idea. So how long does it take to search one page? Well, in order to, the execution time of this attack depends on whether we are lucky or not. Well, if we are lucky and we find this pattern in the first page, and it will only take like 0.3 seconds. But if we need to search other additional pages, one extra page will take about 58 microseconds. So the execution time of this attack depends on how soon can we find this page with this pattern. Well, this is basically a demonstration of this attack. So here, you can see that this attacker is trying to log in remotely to this OpenSSH server. And because the attacker does not have the password, so he can try many times, but he cannot log in. And then the attacker gives up. So next, the attacker will go to another virtual machine that is controlled by the attacker, which is co-locating with the victim, and conduct the rowhammer attack and also the page table replacement attack. So here is the process to search the pattern in the physical memory. Okay, once we have found this pattern, here we are pretty lucky here, and then we just replace this string with a different one. So we change the memory content. And now the attacker can try to log in again. And here, without entering the password, the attacker can log in the OpenSSH server directly. Okay, so to summarize the state of the art of the rowhammer attacks, so in terms of attack scenarios, there has been cross-VM attacks. And in this paper, we show that we can do the cross-VM attacks in Xen PVMs. And there has also been other work show that with HVM, the hardware assisted virtual machines, as long as the virtual machines use memory deduplication technique to merge the memory pages with the same content into a single one, it is still possible to do the cross VM attack. But this technique, with this memory deduplication, is not widely used in public cloud. So the applicability of this attack is uncertain. So and there are other attack scenarios, like in browsers. It has been shown that the JavaScript code can run row hammer attacks as well. And more recently, it has been shown that on mobile devices, attacker can use zero permission application to exploit the mobile device and get root access to the Android device. And in terms of countermeasures, one easy countermeasure is just to use better hardware, like the ECC memory or DDR4 memory. But it has been shown those two types of hardware can also be exploited by row hammer. Can also attacker has also can still conduct row hammer attacks on those two types of memory. But whether the attacker can exploit the row hammer vulnerability or not is questionable. Okay, we are not sure about that yet. And another countermeasure is the purely software-based defense, which we don't know. We don't know how to do that yet. Okay, this is still an open research question.
So I have a question
Sure.
I have a question about so why it is not working for the non-pair virtualization environment. Is it because simply changing myself in the pair virtualization in the non-pair virtualization environment is sort of the meaningless?
Well, the answer here the reason is that in the pair virtualization technology, the page table is stored in the guest kernel space, but is made read-only. But in the hardware-assisted virtualization technology, there are two levels of page table. Simply changing content of the page table inside your kernel memory does not help in this process. There's one additional layer of page tables.
Then, assuming that we are in the non-pair virtualization environment, is it possible that they are in the same bank? The different roles are actually assigned to the different the VM instance. Is it possible?
I believe so. I believe.
Oh, then there is still a possibility to launch the row hammer attack.
I believe it is possible to launch this cross VM row hammer attacks on in HVM environment. But the problem is that whether we can deterministically exploit this vulnerability or not. That is a research question. Okay, I'm going to try to wrap up my talk here with this question: when side channel meets row hammers. So side channel attacks is a type of confidential attack, and row hammers is kind of like an integrity attack. They are similarly so different, but if you think more carefully, they are actually not. So here we are trying to. This is ongoing research. We are trying to build a attack prerequisite graph here. Try to identify what is the requirement of conducting side channel attacks and the row hammer attacks in the operating system. You can see that some of the requirements to conduct both attacks are very similar. Like sometimes if you have fine-grained time measurement, and that will enable a lot of timing-based cache side channel attack, and that will also enable a DRAM address mapping, which will help you to build a double-sided row hammer attack. And similarly, if you have the ability to translate the virtual address to the physical address or to the real machine address, then it can help to reconstruct the DRAM mapping and also be used to conduct the prime probe based attacks. And here another example is the physical page sharing. If the attacker and the victim share the same physical pages, on the one hand, it will enable a reuse-based cache timing attack. Well, reuse-based cache timing attack is just another term for the flash reload attack, okay? Because the attacker and the victim share the same physical page, and it also enables a type of row hammer attacks. Because on HVM machines, as long as the memory deduplication is enabled, the attacker VM and the victim VM can share the same memory page, and because of this physical page sharing, it is possible to change some critical code or data to conduct the attacks. Okay, so this is still ongoing research that I'm working on right now. So here to conclude that when the mutually distrusting parties share the cache and memory hardware, it may be a security concern. It can breach the confidentiality, integrity, and sometimes the availability of the computations. And there are solutions to this problem. One immediate solution is to design new hardware, to enforce hardware-level isolation. Well, alternatively, we have to conduct some software-based isolation. And my perspective here is try to eliminate the necessary condition of all types of cache memory attacks altogether, trying to prevent these attacks as a whole. Okay, this is my conclusion. Any questions?
About the flash reload attack, is it possible to first feed the cache with the dummy data?
So your question is, in the flash reload attack, whether it is possible for the victim or for the attacker?
For the attacker to feed the caches with the dummy data and then.
So what is the purpose of doing that?
The same as the flash instruction. So does that have the same functionality as the flash instruction?
So by filling the cache with dummy data, you are expecting a victim to evict some of the data.
Yeah.
Okay, so the answer is that this type of attack is called prime probe-based attack, which is not the topic of this talk. But again, this prime probe-based cache attacks is very effective, and it can be used in cross-VM environments very effectively. Any other questions?
I have one more question about this Linux kernel's privilege escalation of text status. So is it possible that with this what is that latest Linux kernel with the latest CPU, is it still possible to launch the low-hammer attack to do the privilege escalation?
I think the state of art here is that the Linux community is actively trying to find new solutions to the low-hammer attacks.
But still just no?
I do not think they have come up with the idea yet.
And it seems like your the page table replacement attack can be sort of used to do this the privilege escalation for the Linux as well.
Well, we have different assumptions here because in the cross-VM setting, the attacker can control the guest kernel, so the attacker can manipulate the kernel. Manipulate the page table to some extent, can read the content of page tables. But in the privilege escalation attacks, the attacker does not have access to the page table directly.
But the is it essentially? How to put this? Oh, I see. The page table the address is actually in the kernel space.
The page table
yes,
is
yeah,
actually in the guest
yes.
kernel's address space.
I see, yes.
And the attacker can access to this page table directly, but just not be able to change it.
I see.
Okay.
So still, I kind of feel like then the Linux is kind of broken at this moment. Anyone can do the privilege escalation. If that the DRAM chip is kind of vulnerable to the low hammer.
Well, I think so. But I think that is the reason why we have to work harder to try to find out software defense techniques to prevent such attacks.
Okay, let's thank the speaker.
Thank you very much.